Yeah. Okay. So the most important part was not recorded.
I'll present it this afternoon.
Sure.
I can
Yeah,
present
I
it
have
this
my own
morning. I can
session.
present it this morning too. I mean, if you guys want.
Let's see how, I don't know how it's been organized.
Since it's recorded, then I don't have to do it this afternoon. I'll be done. I met my fathers in Paris, so it's not the most convenient.
Okay. Well, at least time-wise.
Yeah, I didn't have to wake up completely. Although I just came back from Vietnam yesterday, so it's pretty crazy.
Oh, okay. So did you go actually to Tara?
Tara is we're going in the end of the week. Yeah, I did go on a leg, but Tara is coming back to France this Saturday. And yes, I'll be there with 4 other people in my lab.
Okay.
And the next Tara mission is around Europe. So this is starting April.
But you did this training course in Greece, you wrote me once. That was for skipper being a skipper.
So that's just my wife and I.
Okay. I thought
practicing for retirement.
Okay. Very good.
Hello.
Hello.
Hello. Hi. Okay, it's time to start the session. Hello, everyone. Welcome to attend the session at the 6th Ocean Best Practice Virtual Workshop. My name is Cheng Xue. I'm serving as one of the moderators for the session, and then pass it over to our UK, who will take over in about 1 hour to lead the panel discussion. This is the first of 2 sessions today. The other session will be at 16 o'clock UTC today and has the same agenda to accommodate people in different time zones. The session is convened under the Observing Air-Sea Interaction Strategy, or OASIS program of the UN Ocean Decade. OASIS is a community working to harmonize observational strategies and develop a practical integrated approach to observing air-sea interactions. OASIS is organized into 5 theme teams, one of which is best practice and interoperability. The benefits of following recognized community best practice are numerous and fundamental to the sustained global ocean observing effort. OASIS seeks to address regional platform and accuracy gaps in observations to create a more sustained observational network of air-sea interactions that will be capable of addressing strategical, temporal, and spatial scales for climate and weather prediction. The OASIS best practice and interoperability team aims to identify, create, and promote best practice in all areas of air-sea interaction in support of the OASIS goals and the UN Decade of Ocean Science for Sustainable Development. The current co-leaders of the OASIS best practice team are Juliet Hermes, Jack Reeves-Ayer, Wilkinson, and Cassie Wilson. I'd like to acknowledge them and all the team members. I also acknowledge OBPS committee team. They have done a lot of work for many weeks for this session. Starting in 2020, an international group of scientists began accessing current standards for measuring shortwave and long-wave radiation at sea, finding that many land-based best practices are unsuitable for marine environments. The group used community workshops and collaborative writing projects to compare alternative best practice applicable to a variety of marine observing platforms. In the session this year, we will hear from scientists who have recently developed best practice for surface radiation and ocean color measurements. They will share their stories about the scientific and organizational aspects of best practice development and talk about their next steps. We will also hear about the newer best practice work in the fields of direct coherence fluxes, including the current state and what is needed going forward. We hope the sessions will help newer best practice groups gather momentum and also propel established best practice towards endorsements and widespread adoption. While the discussion will center on process as the air-share interface relevant to OASIS, we hope the lessons will be valuable for all in the ocean best practice system community. Here, we encourage everyone to sign up for OASIS and the best practice theme team if you aren't already, and then look out for and respond to future emails about working groups on different variables. You can access the Get Involved link at the upper right of OASIS homepage, and you can also email the best practice team leader directly. That will get you a date to email list that we will use to organize future or working groups and events. The web link and the emails will be sent in the chat window later. The duration of the event will be 19 minutes in total, including 60 minutes of presentations and 30 minutes for discussion. And now we will have a series of speakers. I want to introduce to you the first speaker, Juliet Hermes. She is one of the co-leaders of this session. We will hear about the overview of OBPS endorsement from her. Hi, Juliet. You will have about 10 minutes. Juliet, it's your time now.
Okay. Just gonna share my screen.
Yes, I can see your screen.
Just putting it into presentation mode there. Can you see the presentation mode?
Yes. Yes.
Okay, great. So thanks so much for the introductions. And this morning, I'm just going to give a very brief overview of the Goose Best Practices endorsement process. And I'm going to start the presentation with a little sound bite. So if you don't hear anything, just say, otherwise we'll all be sitting here in silence. It's from one of my team about their experiences with best practices.
On the brink of a cruise on board South Africa's research ship, the SA Gallus II, I was informed by my team that we required an epibenthic dredge for the collection of biological samples. As instrument technician, it was my responsibility to identify a suitable design and ensure the timely manufacture and delivery of the equipment. With sailing date looming and having no prior experience in dredge design and deployment, I frantically searched the internet for any guides that could assist me with the task at hand. Fortunately, I stumbled across a marine sampling field manual for benthic sleds and bottom trawls, and the mesh recommended operating guidelines for trawls and dredges. These guides not only gave me a detailed breakdown of dredge dimensions and deployment protocols, but even went so far as to describe sample preservation and post-cruise data management. It definitely saved my field work, and I have since used them on numerous other cruises.
Oh,
On the brink of a cruise.
there we go. Okay, so that was one of my team, a benthic biodiversity technician. And I think, what he was saying there for me really highlights a few things. Firstly, it really shouldn't be that you're struggling and searching around in the internet to find best practices for the field work that you're wanting to do, and that's sort of really where the OBPS system comes into place. But, for him to get an understanding of, like, he found all these different things and he didn't know which one to use. And so that's where this Goose endorsement process has come into place to really kind of highlight what has been fully recommended. And the other nice thing about what he was talking about, I think, which isn't really that relevant to the endorsement, but the fact that, he was using an Australian best practice for the work that we're doing in South Africa. So it's really just the sort of sharing of best practices within our communities, nationally and internationally where it's relevant. So I'm not going to dwell that much on the ocean best practices. I've put the website up here. I mean, we're all at the workshop, so hopefully we all are familiar with the website and the project itself. So it's the Goose IODE Ocean Best Practices System. And it's an IOC project which was approved in July 2019, and it's co-sponsored by Goose and IODE. And it basically supports the sharing of methods, handbooks, best practices, standard operating procedures, and we work very closely with the ocean community across the value chain. And as I'm sure you're aware, Johannes here is one of the co-chairs. So what I'm talking about today is really the Goose endorsed best practices. So basically within the Goose best practices system, best practices have been harmonized and adopted across components of the sustained ocean observing system within communities. So for example, within the observation coordination group's global ocean observing network, you've got the Argo program, you've got GLOSS, GoShip, HF Radar, and all the others. And also within expert groups and networks under the Goose Ocean Observing Panel for Climate, you've got the Goose Ocean Observing Panel for Climate, the OOPC, the Biogeochemistry, or the BioEco panels, and also the expert team on operational ocean forecast systems. And so these best practices have been developed within each of these Goose components through a really structured community review process, and they've been adopted as global methods by that particular relevant ocean observing network or community. So they're basically viewed as globally recognized best practices, but that they've really undergone a rigorous process of community review and consensus building. And that's really the key thing within the Goose endorsement process. And this has been for a specified application or an essential ocean variable or biodiversity variable or climate variable. So any of the essential variables, the observing platform and the sensor. And these broadly adopted community best practices can be viewed as tested methods that are fit for purpose, defined, and they fully satisfied the definition of the best practice, which is highlighted on the OBPS system. So Goose are really actively encouraging the communities to develop these best practices across the entire life cycle of the ocean observation. So from mission design through to delayed mode quality control. But these best practices, they might not be sufficiently or broadly visible, and it may not be clear when you come across these best practices that they've been through such a rigorous community process. So really between the Goose community and the OBPS community, that there was this need identified to be able to discover these best practices that have been recommended and adopted by the Goose and the Observation Coordination Group community. So really, this is just highlighting why we need Goose best practices endorsement. So I think this is really what I've spoken about. So what do you have to do to qualify as a Goose best practice? So you have to have completed a rigorous community review process, but the comments need to be publicly invited, but they also then need to be actioned by the author. So you need to be able to really show this review process and how you've then actioned on the comments. And then after the review, the whole best practice needs to be approved by the leadership of the relevant network or the expert team or other community leaders. So for example, if you had a best practice on something around radars, you would then need to approach the HF Radar observing group. The best practice needs to be fit for purpose and fully satisfy the definition of the best practice, which is on the OBPS. And then it needs to be recognized through the relevant Goose body. So through the BioEco panel, the BGC panel, the OOPC, or through the Observation Coordination Group or ETOOFs, after it's been approved by the relevant network leadership. And then following that, the best practice needs to be available and identifiable within the repository, or that it will be submitted as soon as the endorsement is received. And then there needs to be a commitment to really update that at relevant timeframes. And also, what we'd really like to encourage is that if this Goose best practice is published, if it's not published through Frontiers research topics, but that it is published in open access journals so that it can be taken by, by everyone. So this is just 2 examples of best practices that have been through the endorsement process. This one on the left was endorsed through the IOCCP and GoShip, and then the one on the right through the BioEco panel. So basically the process they followed was that the best practice was created by the community. There was then a full community review and the feedback was taken up. It was noted and it was agreed by, so this example here was agreed by both IOCCP and GoShip that it should be Goose endorsed. And then a sort of Goose endorsed certificate was prepared and it was put in the acknowledgements. And also then when it's submitted to OBPS, it has this endorsement certificate and a search. So when you search for Goose endorsed, it comes up there. And then the same steps happened on the right. This paper had actually already been published, but an affiliated best practice was then uploaded onto the BPS. So just in summary, really asks to the community are to continue to work on creating these best practices where needed, or to begin to converge best practices. To involve international reviewers where possible to really try and make these best practices relevant globally, to make them openly available, and to identify if you have key best practices as part of your group, to really sort of say, well, we want these to undergo the Goose endorsement process, and then you can just reach out to me for further discussions on how to do that. And that is me. Stop sharing.
Okay, thank you, Juliet. Let's move on to the next topic. The next topic is surface radiation. Is surface radiation, and the speaker is Daniela Moloni. She is from Italian National Agency for New Technologies, Energy, and Sustainable Economic Development. Hi, Daniela. You will have about 15 minutes. Let's start.
Okay. Good morning, everybody, and thank you very much. Can you see my screen?
Yeah.
Yes.
Yes, looks good.
Okay. I'm giving this presentation on surface broadband radiation measurement best practices, which is mainly produced by Laura Rimaki, and she will be giving the same presentation in the UT afternoon session. Okay. The scope is to collect as much as possible accurate measurements for surface broadband radiation budget and many other applications from instruments that are mainly deployed on different platforms, like fixed towers, ships, moored buoys, uncrewed surface vehicles, and drifters. The motivation is supporting the expansion of ocean networks as part of the OASIS. Here is an example of the expansion of the Tropical Pacific Observing System from an array of 4 reference buoys with surface radiation measurements to all of the 55 buoys, and with an upgrade of the radiometers model. The motivation is to merge the land and ocean measurement communities, because most of the Earth's surface is covered by oceans, but we all know that over land there are many established networks of surface radiation measurements. For example, the baseline surface radiation network. But we know that BSRN requirements cannot be met on most ocean platforms because they move, because they drift, they tilt, they are unattended, and most of them have a power limitation. And moreover, over and ocean surface radiation communities have evolved separately in time. So the radiation best practice timeline starts in 2020 with an early discussion at the GOOS-GGOS meeting, and during an EGU session connecting land and ocean radiometry communities. The first ocean best practice workshop in fall 2020 had as main outcome the development of a report from Megan Cronin and Laura Rimaki, which collected inputs from several people of different communities. The outcome of the second workshop in September 2021 was a paper coordinated by Laura, and she produced this paper draft after the workshop, again gathering inputs from all the people involved, and iterates through several drafts. Then Laura presented the outcome of the workshops at several meetings, and the future plans are to submit the paper by winter 2023 to get the GOOS endorsement, and moreover several experiments have been planned. So the recommendations from the first meeting were to compile a list of papers showing the performance of different sensors, to develop a decision tree for the choice of the best sensors based on the aim of the measurements, either surface radiation budget measurements or for biological studies and so on. And then to develop best practices for surface radiation observations, to propose the expansion of the land-based calibration facilities in order to handle ocean-based sensor systems, and also to propose intercomparison experiments at ocean land testbed sites, for example, near shore and land-based tower references, like the one we have in Lampedusa. And here in the bottom, you can see the report of the first workshop. And then, as I told, after the 2021 workshop, Laura started preparing the paper on ocean radiometer best practices. And here you can see an example of what we have to deal with when we want accurate radiation measurements. The table shows the characteristics of a class A pyranometer. And in the graph, you can see an example of the bias that is caused by the cosine response of the pyranometers in shortwave irradiance measurements. And then a list of studies and experiments for future best practices has been developed concerning fine corrections for mean and wave-induced tilt based on, for example, SPN1 measurements, and experiments to quantify how the lack of ventilation and shading in pyranometers on ocean platform can affect long-wave irradiance measurements, and to evaluate and improve albedo, surface albedo parameterizations as a function of solar zenith angle, ocean color, and wind speed, and to use UAV in order to improve measurements of reflected solar radiance and emitted long-wave radiance, to develop recommendations, for example, for sampling rate standards for ocean-based platforms. And also very important is to quantify the impact of lack of cleaning of sensor domes in unattended platforms, and possibly to find a relationship to be developed for deriving the impact of dirt as a function of time unattended. So the next steps are to submit the paper for to be published in Frontiers in Marine Science, and to get feedbacks from different stakeholders in the next meetings, as has been done previously, to have the good endorsements for the best practices. As I said, to plan intercomparison experiments to determine and evaluate the impact of these best practices and the use of new technologies. And in the future, it is important to determine how to integrate land and ocean radiation datasets to make them more useful to the whole community. And finally, Laura wanted to report what she learned as a main coordinator of the group. So she had positive points in involving different people from different communities, and inviting people to present their measurements and their methodology during the workshop sessions. And the notes from the first workshop became easily a report that was iteratively written, and with a contribution from different people. And then an advice for those who are going to start a new best practice. She advised to have one or two primary leaders for writing the best practice document and leading the workshop, and having to identify sub-leads for each section. And also she find helpful to have a roadmap of the end goal of the paper. So thank you very much.
Thank you, Daniela. Now we can have one or two quick questions. Are there any questions for this topic?
I have questions if there's time. Manuel here. Can I ask?
Yes, please.
Yeah, so Daniela, very interesting. There's a whole parallel radiometry community, as you might assume, that does hyperspectral radiometry, highly spectral measurements. They do PAR, they do UVA, they do UVB, that are not necessarily for ocean heating. It looks like the only instruments that you're interested in are the long and shortwave radiometry, which have to do with ocean heating. And there's a lot of work on fiduciary requirement that ESA is doing. There's huge amount of protocols being written on radiometry that are completely decoupled from your effort.
Yes, mainly we focused on broadband, shortwave and long-wave radiance measurements, but also, for example, in UVA, in UVB, and in photosynthetically active radiation measurements that are very helpful for biological studies. Yes, the main focus is this, but of course, best practices should be very, very useful for all the spectral and hyperspectral measurements that are from surface that are strictly connected with satellite missions. And
but again, the physics satellite mission are seem very decoupled from biologically oriented satellite mission, unfortunately. I think that somebody like Robert Frouin from Scripps will be extremely useful on your committee, because he has done, he's involved both in European, Japanese, American protocol of PAR, UV, is involved with many satellite missions, and somebody like this can really connect with the other committee. So the name of Jeremy Waddell, but Jeremy is so busy with space now, I don't know how much he was able to contribute. But Robert Frouin would be amazing as a radiative expert to add to your committee.
Okay, thank you very much.
You're welcome.
Okay, Jonas.
Yeah, I had a question, or a comment actually to what Emmanuel just said, or actually two. So the first comment is, Emmanuel, it would be very, very important, and for the whole process, if that community you were just referring to would deposit whatever they have in the ocean best practices system.
It is deposited. It's deposited via the IOCCG. I don't know if the ESAC documents are there, but
Well,
everything the IOCCG does, including report on radiometries, have OBPS ODIs.
okay, so then it has to be in there, everything that is
Exactly.
the
And
repository.
there's recent
receives the
one
UI.
from Gibordi and Ken Voss. There's a whole variety of them that have been done that have OBPS ODIs. Yeah.
Okay.
But the problem is radiometry is divided between communities that use it for different practices.
Sure.
And the physicists tend to have carved the long and short waves because that's what influence heatings. The ocean color deal with PAR. Now we deal with UV because space has UV. We deal with spectral, highly spectral radiometry because that's what influenced the color we see from space. So it's they really fundamentally the measurements are identical. Just the way the integral bands are different and how you weigh the different bands.
Sure.
But they're really dealing with the same problems.
Okay, so
there's a lot to share. We don't have to
informatics sense, it would be the metadata actually that is relevant here. Exactly. The metadata that comes with the document is apparently that what determines, say, if Daniela is having a group, right? Yeah. One thing that we, as an OBPS, Ocean Best Practices system, provide to the community is the repository. And the repository is where you should first search for whatever you are after, right? So if you're after PAR measurements, satellite, then you type in the two terms and you will get a list of everything what's in that repository that relates to these two, and then you can combine further things. Well, okay, and then the second comment, and that also addresses something that you, Emmanuel, were writing in the chat, that is this endorsement. The endorsement is actually something that saves a lot of time, because what you can do is you can say, well, there is this 1 or 20 different best practices from a different community that exactly match what we want. So we can endorse these documents as being the applicable documents for OASIS. And that is, and you can always do that. And there's no need to have a GOOS endorsement. This is just one community, but you can, and you should probably, define an OASIS endorsement. What are the requirements for OASIS to endorse documents? Later, that could be also integrated into GOOS, but first you should concentrate on your community, what you think is important for these documents to contain. And then if you identify documents in a different community, you can say, well, this fits exactly, endorsed. And later, 1 year later, you think, well, it doesn't fit too good, so I will do some corrections here and come up with a slightly different version, which is now your new document and a year later, and a year later. So this is the whole idea behind this endorsement. And yeah, that can be propagating into GOOS eventually, but it's not a need, right? It's first of all for your organization. Okay, thanks.
Okay, thank you.
Okay.
Can I add to that quickly? So just to add to what Johanna said, the Goose endorsement process it's set up in a way that you should be able to just utilize the same process for OASIS. So if the way it's done fits for how OASIS would like to endorse documents, then the process can be very similar. You just change where it says Goose endorsed to an OASIS endorsed. Yeah.
Okay. Let's move on to the next topic. Just it's your time, and you have about 10 minutes left. Hi, Jonas. It's your time. The next topic is ocean color.
Is that me?
Yeah.
Okay, so I will not talk about ocean color actually, so that you misunderstood. But it doesn't matter. I think I will give some examples and I will share my screen. And to be honest, I never saw an agenda. That's why maybe. Okay. So wait a second. I think you will see the wrong, or you see the right full screen.
Yes.
Yeah, very good. Okay. Oops. So I will provide you some examples for the creation of best practices. And before I do that, before I do that, yeah, my name is Johannes Karsten. I'm from Geomar. I'm a physical oceanographer, seagoing physical oceanographer in Germany, and I'm also the co-lead with Julian on the work package for convergence and endorsement in the IOC Ocean Best Practice System Steering Group. Good. Before I really come into the details, I think it's important to emphasize again what best practice is. So that has actually two components to it. One is that you define something, a methodology that has repeatedly produced superior, better results than other methodologies which address the same objective. Right? So if you do something better, then some other people that propose also to do something, then this starts to qualify as best practice. But what is also important is that you will need to review this document with expert groups, with multiple organizations that also adapt that process. And also, yeah, it's then automatically, because it's a trusted process employed by multiple organizations. So best practices are actually created by the community for the community. So how does it work? How to create these best practices? I think from the discussions we had before, it seems like it is clear already how to do that. I still would like to go a little bit more detailed on it. And this is being done here by this little infographic. So what the first step actually to do in creating ocean best practices or atmosphere best practices is that you confirm a need, right? So you need to understand, why do I need to really have these best practices, or is there a need? And then, okay, the need is one thing. Then the other thing is that you need to form a working group that cares about that need. And most importantly, you need to identify leaders that take it on, really the heroes, like Emmanuel, for example. And then these leaders will invite contributors and so forth, and you set up the whole thing. Then is a part that often is the focus. So the first part is actually being done automatically, often not with that many thinking. And now we come to the core part, which is develop the content. The development of the content, of course, depends a lot on the composition of that working group, because it is a knowledge base. And if the knowledge base is not comprehensive, the document, the content will not be comprehensive. So if that has been done, then you review that draft, you have reviews and so forth, you release it. And the release actually then also should have many, many people involved that will review the document after the release. And there's a process in really reaching out to a large audience. Then what comes next is really this important step to invite feedback on the release, to do surveys, to publish it, to assess what is the outcome of it. And then after that has been done, you get the community to endorse it, to find it good, like the OASIS endorsement, for example, that we just talked about. And you then, in regular intervals and whenever is needed, you revise the document, forming a new working group and go through the steps again. And what actually the IOC Open Best Practices system can do, it can help in this little infographics you see here, the little icons, it can help at certain pieces of this process. As I said before, we have a repository, we have some themes, training, and also user support. One of the examples I would like to give you is that there is a document which is called Towards a Best Practice for Developing Best Practices. And that document actually outlines you how to do this best practice development. And it touches on the different pieces I was just talking about. It has templates on having the mandatory sections of best practices that really address the needs like data formats and uncertainties, all that stuff, and for certain best practices. So now I come to some examples for the creation of best practices by expert groups. And these are from Geoscience Australia, the Australian Marine Sampling Best Practice, the SCORE Working Group 154, where Emmanuel will say a lot more, I believe. No, he will not. He will say mostly about the satellite stuff. And the Ocean Gliders Coordination Network that developed SOPs actually for glider operations. So coming to Australia. Australia Marine Sampling Best Practice. What you see is a map of Australia, obviously, and you see many, many marine parks here actually that all had in the past own operations, own field manuals, own ways in doing observing for marine protection and for the marine areas. Of course, there was then a process initiated by the Australian governments, by Geoscience Australia, to synthesize, to converge this wisdom that's all around Australia into standard, into best practices actually for Australia. One could also say these are best practices that are endorsed at the end by Geoscience Australia to be the ones that are needed for the operations in the Australian waters. And this is a busy slide, but it doesn't matter. Just see in the middle, these graphics, these are field manuals. So they develop field manuals for AUV operations, for everything that you can imagine for the operations in this marine protected area. And then they have, of course, the content actually is then these individual field manuals with some front matters like introduction and so forth. And then they have also appendixes in each of these field manuals that outline examples, technical advice, and so forth. So how have these best practices, this package, how has it been developed? First, they formed a working group, of course, all motivated by Geoscience Australia. And of course, these are all people that are paid for doing it, right? So they developed the working group with some leads. They developed the content. The working group was then consulted again. a straw man was being created, and that was an iterative process until the straw man draft was in a state that it was completed as a draft. This draft was then sent out for internal and external review to a wider community. And the package I was just showing, all these documents, was released. Then field tests were done with feedback being asked for. That was assessed, the content was revised. Internally, it was again restructured and appended. And then at the end, the final version of this field manuals was released in 2018. Okay, so after that, of course, people were still paid for that. After that, in 2020, there was actually a second version released because over the 2 years, certain things came up. There was actually one more new best practices needed for imagery. And they also changed, corrected, updated as a result of the stakeholder feedback. So people were using the best practices and felt, well, this is not very good formulated, or this is missing, and so forth. So again, they released a new version, and actually that version is an online version, which makes it easier to then do the version number 3 one day. Okay, so I'm really now running short in time, I believe. So there's working group 1, score working group 154, integration of plankton observing sensor systems to existing global sampling programs, POPs. The motivation for that group actually came out of a meeting that was organized by WU's the IMSO workshop that took place in 2017, and which was about multidisciplinary observing in the global ocean, and what are the kind of low-hanging fruits and how can we go about it. And fortunately, Emmanuel and Anya Wade stepped up as heroes to guide a group to address the plankton observing as an emerging or as a low-hanging fruit for the global ocean observing system. So they had funding actually from SCORE for travel a bit, for publication costs. And because it was a SCORE group, there was also indirect funding. And that is very important in the whole process, in particular in groups like the one here, the OASIS group. You have indirectly staff money, right? People spend time on that, and that costs. Then there was a core team being created. The members, 8 actually from different countries, and then associate members, 7. And this is a particularity of SCORE. They require you to have many different countries involved. Without that, you will not get your SCORE group funded. And that actually is very good for global convergence because you get many different opinions from all over the world integrated into your best practice or the SOPs you're developing. So the tools that were used were in-person meetings, actually 3, and then the work on shared documents, and also I think there were virtual meetings as well. The outcome were really 4 publications. Great thanks to Emmanuel, who really drove that. And 2 were actually further work as really preparations for further best practices in the GOOSE context. For Ocean Sites, which is a global ocean long-term time series coordination network, and for GOSHIP, which is a global ocean ship observation coordination program. Then very briefly, another one, which is the ocean gliders. So underwater glider SOPs. Motivation here came from actually 2 EU projects that had deliverables, and these deliverables needed to be written. But WU's also requested ocean gliders to prepare best practices. The leads were actually a number, but the overall coordination was one guy, Sören Thomsen from France, who actually left now the science field, unfortunately, but various SOP leaders that took on the burden to really coordinate the integration. Then funding came, of course, from the EU project for travel. Virtual meetings also cost something, like the virtual chat that's used here, and publication costs as well. And then again, staff money, indirect. There was a core theme from the various experts motivated by the funders and the coordinator, and the tools actually were virtual meetings, and they set up a GitHub that you see on the right that really tracked the whole process. And I think that was a very interesting approach for convergence in a virtual space. The outcome are various SOPs for option and salinity and so forth, and also for data format. So last slide, my view on what is needed to have OASIS expert group carrying out the convergence process is you need a motivation and leaders, actually the heroes like Emmanuel. You need some kind of support. There's no way around that. You need some money. And is it only for the meetings? Then there are certain tools that need to be really used in a clever way. Is it either GitHub or G Drive or whatever? You need to work on shared documents. And you can, tools are also, as I outlined it before, the OBPS, the Ocean Perspective System, can provide you tools and help through our repository, through templates, and also through advice. And importantly, I mentioned it also before, define an OASIS endorsement. I think it is a little more than just taking the GOOS endorsement. You really need to identify what are your needs for your documents, and then define them, write them as a document, and then you can really, for example, use WMO regulations and best practices, maybe already as OASIS endorsed. Thank you very much.
Okay, thank you. Because of time slot, we will discuss the questions in the discussion part. Now, let's move on to the last topic. The last topic is direct covariance flux. The speaker is John Presser. He is from Stockholm University. Hi, John. You will have about 10 minutes. It's your time now.
Okay, thanks, Shane. Okay, let's see if I can share this. Okay, is that working?
Yes.
Yep, great. Okay, yeah, thanks, Shane. Yes, so I'm from Stockholm University, and I've very recently come to this OASIS group to really kind of get it started now with James Edson from HUI. So I'll go straight into this kind of talk. So these photos at the top show some typical platforms that we use to measure these direct covariance fluxes. We've got the Swedish icebreaker Odin here with its kind of foremast just visible, and then this is the instrumentation at the front of at the top of the foremast. So this is a kind of typical eddy covariance setup. We've got a sonic anemometer, infrared hygrometer, and various other kind of meteorological instruments. And these other photos are a couple of other platforms that are used for this kind of work. There's a sail drone with a just visible a sonic anemometer at a few meters height, and an OASIS spar buoy here again with a sonic anemometer on the top and about 5 meters above the surface. Okay, and then what we're trying to do with these instruments, of course, is measure these turbulent fluxes. So I won't go through these equations in detail, but this is, I guess, the main fluxes we're interested in: the momentum flux, the transfer of wind energy into the ocean, the buoyancy flux, or the sonic temperature flux equivalently, and heat fluxes, latent heat flux and sensible heat flux. And of course, there's also gas fluxes, which aren't shown here. So kind of mass fluxes, in effect. And then often what we're trying to do, we want to determine these fluxes themselves, but we're also, when we're making these type of measurements, we're often looking to improve these parameterizations of the transfer coefficients for these turbulent fluxes. So like the drag coefficient, the Stanton number, and so on, which are then used in kind of numerical modeling to represent these exchanges, or equivalently to allow us to determine these fluxes on a field campaign without having to go through the trouble of measuring the turbulence ourselves. Okay, so that's often what we're trying to do. And then the big challenge is with doing this at sea, there's two main kind of challenges which we'll come to. That's the flow distortion, the effect on the flow by the platform that we're measuring from, and the motion of the platform itself. To measure these turbulent fluxes, we must measure the vertical component of the turbulence, and it has to be the vertical components. So we need to correct our wind vector to take into account the fact that the platform is moving around all over the place and is moving up and down with the wave field. Okay. So it used to be a variety of different instrumentation we used to make these kind of measurements, but nowadays it's almost for the wind measurements, it's almost entirely done by sonic anemometers. They've become robust, reliable instruments. So recommendation of what type of instrument to use is a relatively straightforward part of this work. But there's many different models of sonic anemometer. People, I think there's going to be people have different preferences for which ones. I've just put my own ones here, but I think there's people will probably disagree on some of this. And there's different models that are suitable for different conditions. For instance, freezing conditions, as kind of shown in this photo, is normally better to use some kind of heated model. Some of these models have their own additional corrections which are required depending on what calculations are done internally on the sensor. And another thing I should highlight is depending on which one of the direct covariance fluxes you're interested in measuring, there are different challenges. For measuring the wind stress, the drag coefficients and so on, or the sonic temperature flux, then there's a lot of experience or community experience there, and it's relatively straightforward in terms of the instrumentation. A single sensor is used for both these fluxes. If we want to instead measure the latent heat flux, that's a bit more complicated because we need an additional sensor, hygrometer, and typically these have to be these open path type sensors, such as shown in the photo at the front here. And in most kind of ocean going situations, these require cleaning of the optics during the deployments. They have higher power requirements than the sonics, so there's additional challenges. And then if we were interested in measuring gas fluxes, there's even more of a challenge. This kind of schematic down here shows a kind of typical modern setup for measuring gas fluxes. So we have the kind of the turbulence instrumentation, but also a whole system with intakes and air dryers and filtering. This system here has a kind of nitrogen puff system for determining the lag time for the gases to be drawn down, all this system to the analyzer. So it's a complicated setup, and it also has a much higher power requirement. So typically these are almost entirely still deployed on ships rather than on buoys. And there's going to be, I think, a separate SOLAS community efforts on developing best practices for the gas fluxes in the near future. So I think as part of the work here, we will leave that part of this direct covariance and leave that to them. Okay, in terms of the other kind of measurement requirements for doing this, so these direct covariance fluxes, the theoretical underpinning from it, a lot of it comes from similarity theory, from Mononovikov similarity theory. And the kind of key parts of that are that, or some of the key parts of it are that the turbulent conditions be stationary and homogeneous. So in a mean sense, the turbulent properties are relatively constant in time and space. Of course, this is never 100% true, but is kind of largely true over the open ocean in particular. But then in other situations, like in kind of coastal regions where land is present, or in kind of polar regions where there might be sea ice, these conditions may not be true. So the theoretical kind of assumptions are called into question. We also, to make these measurements, we need to be sampling within the surface layer, which is normally given as the kind of roughly the lower 10% of the atmospheric boundary layer. And again, over the open ocean, this is almost always true, but in other regions where we might be making these measurements, this isn't the case. And I just want to highlight as well that these measurements come with quite sizable footprint. So we're making a measurement at a height in the atmosphere, but it's associated with a particular kind of footprint on the surface. And at a measurement height on a ship, which might be, say, 20 meters, this is on the scale of a few kilometers. If we're measuring at much lower heights, then the footprint is smaller, but there's a lot of other issues to deal with. If we're measuring from buoys, for instance. The sampling rates is a key issue. So as we get close to the surface or at higher wind speeds, we need to sample at higher rates to capture all these kind of turbulent fluctuations. And this is kind of shown in this representation of the turbulent co-spectra from Keimel's kind of paper from the 70s. So this kind of upper line here shows the frequency distribution of the turbulent energy in effect. And you see to measure at this point here, highlighted, which isn't at the highest frequency range, but it's kind of midway. If we're at 10 meters height and with wind speed of 10 meters, we need to sample at 2 hertz, which is certainly possible. But if we're down at kind of 1 meter height, to sample at this point, we need to be sampling at 20 hertz. And to get these kind of higher frequencies, obviously we need to go higher. And for higher wind speeds, we'd also need to go higher. So then we're at kind of the limits of what kind of the sensors can realistically do. So something to be aware of, sampling close to the surface. And similarly, close to the surface, we also come up against the limits from how the sonic anemometers are built, that they have a certain path length between the transducers. And this path length has a fixed size and it can't sample eddies, the turbulent eddies smaller than this size. So as we get close to the surface and at higher wind speeds, the eddies that are containing significant portions of the turbulent co-spectrum become below this size. So again, we kind of run up against kind of fundamental physical limits. And also, as we get close to the surface, particularly in higher wind speeds, we might start to become within the wave boundary layers. This is the kind of region, typically from the kind of significant wave height and downwards, where, as well as the wind-driven stress, there are now kind of wave-driven effects, things like pressure stress and so on. These are topics of research in themselves, but will affect the measurements and maybe cause you to measure something that you're not intending to. Okay, so the motion correction then is kind of one of these kind of key parts of this, both for measuring kind of wind speed for moving platforms and also particularly for measuring the direct covariance fluxes. The kind of basic technique for correcting this can be reasonably well established by Jim Edson back in the late 1990s, and I've kind of briefly kind of shown it here. So this is the kind of the basic setup to correct your observed winds to be a true wind vector, a true three-dimensional wind vector, or actually to be the wind vector relative to the ocean surface. So to do this, the kind of standard setup is to use a kind of three-axis accelerometers and three-axis rate gyros. Nowadays, the single instruments contain both of these. So we have these kind of inertial motion units, and they're kind of small, relatively inexpensive. So while there used to be different ways of doing this, now the kind of really the best way of doing it is to kind of strap down a sense like this very close to the sonic itself. This minimizes some of the kind of translational errors that have to be made in this correction. And should also highlight that to do this, whether from a buoy or from a ship, you also need to have good measurements of the platform translational velocities, the platform heading and stuff. And this part can often be neglected, but these parts also need to be measured with similar kind of accuracy to the actual motion at the point of the wind measurement. And also, I think one of the key things that's come up in more recent years is the importance of measuring the current speed as well. So this will require an additional sensor to measure the currents, but it can have kind of large effects. So here's an example for one of Jim Edson's papers. So on this panel on the right, we're measuring the drag coefficients, and it's been measured by 2 buoys, one within the Gulf Stream and one outside the Gulf Stream. So the one in the Gulf Stream has a high current flow, and you can see when we're looking at the absolute winds, there's an offset between the two sets of drag coefficients measured by these 2 buoys. But when we measure in terms of the relative winds, so that's the winds relative to the current speed, the measurements collapse together. So we can see that there's, it's important to determine this and to measure these fluxes, these exchange coefficients in the correct frame. Okay. And also more recently, there's been a lot of kind of use and kind of discussion in the community of using an additional decorrelation correction. So here, after we've applied the standard motion correction to our fluxes, we end up still seeing a kind of a signal in the co-spectra, this kind of point here, at the frequencies we associate with platform motion. And this can be removed often with a relatively simple linear regression against the accelerations that have been measured on the platform. Remove this and get a more classical looking kind of co-spectral like this, which has quite a large effect on the fluxes. So this plot here again shows drag coefficients, and these red points are the kind of standard measurements. And then following this decorrelation approach, we get these blue points, which are more in agreement with bulk parameterizations, some of which are determined from platforms which don't have any motion. So that's all well and good. But of course, if we're doing this kind of correction, we're also removing any true wind wave interaction signal, which is also something that people are often interested in. So if we're doing this at heights well above the kind of this kind of wave boundary layer, this is probably an okay approach. But as we get closer to the kind of wave layer, so if we're again making measurements from buoys, this becomes more of an issue. So I think this is something that we could look at best practices about. Okay. And then the other main issue we have to deal with making these measurements is the airflow distortion. So kind of small and large objects such as the ship superstructure airflow and affect both the wind speed, but also the wind direction, the wind height, and potentially for eddy covariance, for the direct covariance fluxes, they might also affect the larger turbulent eddies and therefore affect the flux, the turbulent properties itself as well. That's still kind of an area of research. And to give you an idea of the kind of size of these biases, even for well-sighted instruments, so therefore, you know, I'm talking about kind of 4 masts, well-sighted 4 masts, or kind of on reasonably well-constructed buoys, these biases might be 5 to 10%. That's what's kind of shown in this plot here. This is some modeling of wind speed biases done on a ship, and then compared with measurements where the wind measurements on the ship have been compared with a mast separate from the ship. And we can see that these kind of biases and the modeling kind of lines up reasonably well, at least for some directions. And we can see that this bias kind of varies with wind direction, and even for bow-on measurements is around 5%. And then as we go further off the beam, we get to larger errors, kind of 10% maybe. And I should say that these kind of biases, as well as for ships, this size of bias is also present even on buoys. Things like these larger buoys like this have similar kind of wind speed measurement errors. And one of the challenges here is that these biases also correlate with signals of interest. So with the wave field, with the ship's attitude to the wave field, with the kind of ship operations, buoy movements and so on. So it can often kind of confound analysis when people are trying to relate the fluxes to such things. So another problem, particularly with the drag coefficient, I want to highlight is that because the drag coefficient, something we're often very interested in determining, is both calculated from the wind speed and also parameterized in terms of the wind speed, these biases are much larger for the drag coefficient. So a 5% wind speed bias is more than is a bias of more than 12% in drag coefficients. Okay. There's many kind of methods that people use to deal with kind of airflow distortion, from trying to make platforms that are less susceptible to it, so very low profile platforms, things like sail drone and so on, or from correct positioning on the ship, so from trying to position your sensors on well exposed foremasts that are kind of a good height above the foredeck height and so forth. And then there's, as well as kind of attempting to minimize it, we can kind of use different methods to correct it, such as this kind of CFD modeling, this kind of, or even using kind of wind tunnels for some platforms, although of course both these approaches are kind of time consuming and expensive. We can also use kind of more theory-based approaches, such as kind of this similarity theory equation, where we can relate the standard deviation of the vertical wind speed to U star, and this should be a constant ratio. In this data from Byron Blomqvist from Mosaic, you can kind of see that, and this is against relative wind direction, that we have relatively constant expected kind of ratio here until we get far off the beam, and then we have these huge kind of spikes showing that there's kind of large flow distortion of these wind directions. Although you should note that there's this kind of sinusoidal wave, even in these good relative wind directions, which varies by more than 10%, I would say. So we can see that there is some kind of flow distortion effects, which could have large errors, even at what is seen here as the kind of the good wind directions to measure from. And there's some other kind of more recent kind of corrections to kind of make adjustments for when ships are underway, which can also have a large effect, but I won't go into that now. Okay, so I think I've kind of very briefly tried to give the impression that making these measurements at sea is very challenging, like it is for many other different types of measurements. But I think in some ways, particularly for these direct covariance flux measurements, and in fact, this is the motivation for developing a lot of these bulk parameterizations, to try and avoid people having to deal with these measurements. In particular, the core parameterization may be what some people call the state of the art. These most recent iterations have tried to avoid using ships at all because of this intractable flow distortion problem. Although, as I said before, actually, these flow distortion issues still affect the buoys that were used in driving core. But core and the kind of the highest quality kind of measurements, as shown here, are kind of in agreement even with other much older wind speed only parameterizations, which are often developed from kind of slim masts, fixed masts, which didn't move, didn't have real flow distortion problems. So these are all kind of reasonably well established. But I think one thing that this kind of best practice community could look at is for situations where, in actual fact, it's better not to attempt to make the direct covariance fluxes, particularly for momentum, for determining the drag coefficients, but maybe for heat fluxes as well. And actually, it's better to use these kind of core, these bulk setups, because the challenges, the errors associated with them are maybe more easy to account for. Although, of course, care is still very much needed even if you're just measuring the wind speed itself. And I guess we can make recommendations for that within this best practice community. And there's many other issues with making these measurements that I haven't really kind of touched on, the kind of quality control, which I think is often a kind of an abused part of making these measurements, with far too many kind of mysterious kind of quality control procedures applied. Having a kind of more established setup there, reducing the number of procedures, more reliance on things like using median averaging and so on would be better. Other things like this. And so I guess with this talk and with this, what we're hoping to do is really just start kind of discussions around this and start this process as kind of outlined in the previous talk. And I should just highlight Megan Cronin did a recent kind of review of this, which was quite nice, covered a lot of these points. And I guess the kind of steps then for this workshop is to kind of take that and really try and make some kind of firm recommendations by bringing in a kind of community engagement to this process. Okay, thanks very much.
Okay, thank you for your introduction. Thanks for all the speakers. The next part is the discussion part. Next, Ewa Uki, who is from Japan Agency for Marine Earth Science and Technology, will lead the discussion part. Ewa, I think we will have about 20 minutes left. Let's begin.
Yeah, thank you. So, okay. So today we had 4 invited talks. The first one is OBPS goose endorsement by Juliet, and the second one is Daniela. She talks about radiation best practice, and third one is Johannes. He talk about the development procedure best practice. And the final one is by John, the direct covariance practice. So from now, we will have question and discussion time. So, first of all, okay. As a first, do you have any question in the audience?
I have a question.
Yes.
Hi, thanks to all the speakers. It was really great. And I had a question for Johannes, who was sort of giving this advice of having an OASIS expert group towards sort of convergent processes of best practice. I was just maybe, Johannes, ask you your thoughts. We already have a theme team on best practices in OASIS. So would you see that that is already encompassing this, or are you saying something in addition is required to move such processes along that are more maybe active and focused in specific areas, rather than having the broader theme team on promoting best practices in the OASIS space?
Yeah, thanks, Sebastian. That's a good question. I think you need both, right? So the theme team, I believe, is the entity that overlooks in your network the development, completeness of best practices, standard operation procedures for the operations you envision in your network. So what that group actually, what I think what such a group can do is, for example, defining the endorsement. I would think that you have participants or representatives from the various different operations. Is it using a wave glider, using whatever radiation measurements from this and that? So these people are standing above and coordinating the thing, and they can also define the endorsement, because this is actually communication, I think, even with a higher level of the overall goal objectives of OASIS. Yeah? And then there is no doubt that if you go into the details, say radiation measurements, that you would need subgroups that devote time and have a leader who really then guides that specific community to develop, converge best practices that are OASIS conform. Yeah, maybe the leader, actually, these leads, individual leads, would also be automatically part of the theme, I think. And yeah, that's a structure I could envision would be very good. It is a bit like this ocean glider structure. I think they did it the same kind of along the same path. So that's my
that's thanks, Johannes. That's obviously good reflections, because obviously we've been spinning up the theme teams quite recently, so it's useful to get this perspective of how it would in practice separate out to have a balance between focus but still keeping the overarching goals and strategy of OASIS in mind. So I can see that you need these focused areas, but probably still embedded within the theme team and still guided by the principles of the theme team in general. Yeah. Thanks.
Sure.
Okay, you have next question? Nothing?
Well, maybe I can add one more comment, because just thinking about what you said, I remember also from this glider group and from another European group on Moore time series. The glider group first thought that they will create one single best practice for the operations. So in other words, they would have a best practice that encompasses all these sub things like salinity, nutrient, oxygen, glider handling, whatever. That is something that we can, as OBPS, not advise you to do. So fragment it a bit more, really focus on themes, because that will allow a much easier kind of review process. There's often a delay then automatically implied when you want to achieve too many things, you have too many subjects in that best practices, it will never be finalized. So very good examples that Juliet showed that is the Go ship, which also is it has several sub SOPs like the one also from the Ocean Glider. So you need, maybe that's also something for the theme team to identify the individual SOPs you are aiming for, and then having those being, you know, that's not too generalized. I think that's also an important topic to consider.
Okay, so do you have comment or question on this matter?
Hi.
Yeah, go ahead. Muted.
Hi, me?
Yeah, okay.
Oh,
Please
yeah.
go ahead.
I have a hi. I have a question to John. Is it matter which correction we are doing first, the flow disorder correction or the motion correction? Or we can just at first starting with the motion correction and after that doing on the eddy covariance data, the flow distortion?
I mean, I think this will be something that we'll try and look at within this best practices, because I think the classical approach is to do the motion correction first and then perhaps do the flow distortion afterwards. But some of the more recent work, this kind of by Brian Ward's group in Galway, they kind of the two processes are kind of merged together in parts to account for some of these difficulties when the flow's been tilted and the ship's moving in particular. So then you kind of have to do both together. Yeah, I mean, it's complicated and there's no kind of definitive right answer, but maybe that's something we can kind of put some recommendations for.
Okay, thanks.
Okay, so Emmanuel, you're right.
Yeah, I just added a comment. There's an issue with projects like OASIS and others that their time is finite. They're created for a certain amount of time and then they disappear. While there's certain entities like SOLAS, like IOCCG in the case of my community, and those stays for much longer. And so it's really important to I think, to make sure that the synergy is such that future updates of protocols and all that are easy to happen within the larger community. And I think in your case it's SOLAS, I might be wrong, but if that's the case, this is something you may want to consider in terms of how you interact with them.
Okay, thanks. So any other questions? No. So I have a question to John. So I think that there is many things to do to make best practice for direct covariant practices. So what do you think that what is most needed?
Well, I think on some things, I think there could be some clear recommendations, like the question from Mirona just now and stuff. I think there are some ways to make some. I think there's lots of people who try and do these measurements, and it's starting out to do these measurements. It's there's a lot of challenges. I think it's maybe needlessly hard for people to kind of get started with this. For instance, there could be more code sharing. Maybe there could be that could be more formalized. I think my experience is that within the SE interaction community, there's maybe 3 or 4 sets of, for instance, motion correction code that gets shared quite widely. And a lot of people have different versions of these same sets of codes, but that's a barrier to entry to the to the community. You know, who do you ask for those? There's no kind of clear way of getting that, and which one is more appropriate? Are there any differences and so forth? So I think that could be worked on. Some of the stuff I touched on is maybe more at the research edge of this. So maybe we can't make recommendations on it, but I think some of the more established parts, like the kind of motion correction, we probably could do some useful things. We have been discussing whether there should be an entirely separate best practices workshop just on the flow distortion issue, because it's so large and it's certainly not kind of solved in any meaningful way. And in fact, that led this ongoing discussion we're having about whether to try and make people not do direct covariance fluxes, because often this problem is very difficult to solve. It's not addressed properly in many studies, and kind of leads to very curious results that people try to publish, which are actually, I think, when they, it's tried to relate to some physical phenomenon, but it's actually just a measurement error. And there's decades of work trying to address this, and we haven't got very far, I think.
Thank you. So any other question? So from chat, there's some question to John, from Hong Fan Chi. So we have the buoy with weather sensor above the sea surface, 1.6 meter, and CDD sensor and flow sensor under the sea surface 0.5 meter. What I can assess on sea air interaction?
Well, a lot, I'm sure. But I would be very cautious about, this is what I'm saying, I'd be very cautious about making the eddy covariance measurements from such a platform.
I
think unless you're in very calm conditions and very low winds, you'll struggle to sample the turbulence effectively for this. But you don't need to. You can make these kind of bulk measurements and do kind of air sea interaction in that way.
So, Marcel?
Yes.
Yeah.
Thanks everyone for really interesting talks. I have a question for John. Maybe you said this and I missed it, but given the sort of shift of the community to try and make measurements from autonomous platforms, wave gliders, sail drones, etc., what do you think are the sort of key challenges that these platforms face in making sort of not only eddy covariance but bulk measurements as well?
Yeah, I think things like the sail drone stuff, I mean, I haven't been involved with that myself, but I think it looks quite promising. I think, it's kind of high enough for most conditions. The sensors are high enough, I mean, and it does have reasonable kind of flow distortion properties, but that is still an issue with those. So I think that can't just be completely discounted from these kind of platforms. But I think they are for making. Me and Jim Edson disagree a little bit on this, but I think he's very kind of. This is how we do this kind of stuff now on these kind of platforms, but him and me, we agree that you can't just use these platforms, because for things like gas fluxes in particular, which is kind of a big area, maybe outside what we'll be doing here, it's very hard, if not impossible, to make those good measurements from those platforms. For heat and momentum fluxes, they're probably, I think they are pretty good.
Okay.
I guess this is something we'll certainly go into more detail on in this process.
Yeah, and I mean, this sail is particularly the example of sail drones. There's a big push in the community to use them for, as you say, heat and momentum fluxes. And the issue with flow distortion, for example, like as a new user of one of these platforms, where do you start to try and understand like what can potential impacts of flow distortion or other issues be with these platforms?
Yeah, well, I think that will take kind of, you need kind of dedicated experiments, maybe, with something like a sail drone that could be done in like wind tunnels and stuff. Kind of quantify those biases a bit more. I mean, maybe that's been done. I'm not so super familiar with the sail drones at the moment, so there might have been some work on that already. I think, again, those biases are kind of, if you're just measuring the winds, if you're just measuring maybe the scalar fluxes, it's not too bad. But as soon as you start measuring drag coefficients, you have to be super careful because the errors just get magnified immediately from these wind measurements. Yeah, I mean, it's not something I'm super familiar with either. But I mean, I think, the community is definitely like you say, the community is definitely moving to more use of these.
Yeah. Great, thanks.
Okay, any other question?
I just, on this topic, I just wanted to make a comment, and just as an advertisement in a way. I mean, it's great to have these discussions, but it's also wonderful to have them within an OASIS space, because in the sense you're dealing with best practice on different platforms, but in parallel, OASIS is providing networks around USVs and other platforms to measure fluxes. So when these efforts converge around best practice of specific variables and specific measurements with the networks that are developing to have a global presence for such measurements of the surface ocean, then I think you can really see how the sort of juxtaposition of the community really benefits the space. So it's not a question; it's just a comment that how to have these conversations together more. I think would prove very, very valuable for global flux observations and sort of systematic observing systems.
Yeah, exactly. So we should do many things. Okay. So do you have any final comment? Johannes.
Yeah, along those lines, I also have a comment, maybe also to the theme team. And that goes along with what Juliet was saying about the goose endorsement. So if I'm correctly informed, many of the platforms you are using here don't have a home in goose, right? What I mean with that, there is no home. Like if you have ships, the home in goose is Go ship. If you have moorings, the home in goose is Ocean Sites or DBCP, the Data Buoy Corporation Panel. If you have surface drifters, Ocean Data Buoy Corporation Panel, there is no home for sail drones, or there is no home for what is it? The glider, the surface glider,
the wave glider,
the wave glider. And I think that's true for many of the, say, emerging technology. So I would encourage you to also in parallel work on a process and engage in respective channels, and maybe through Julia, to make sure that there is this home, because at the end, you would like to coordinate things and to propagate your wisdom, and that is also captured in best practices, into the other groups globally through the home in Goose, which comes through these networks. So yeah, just a recommendation or a comment here.
I couldn't agree more, Johannes. And so the USV network that's spinning up, I think, is going to be critical for, to be specific around the surface platforms, the autonomous surface platforms, because we don't really even know the status of where observations are being collected and what kind of observations are collected by the different platforms, let alone the best practice between platforms. And so this kind of network, to have a home, this is what I understand you're alluding to, is to have a home also for these other platforms that have fallen through the crack in that sense, that like Argo and Drifters and Ships have. And so we need you. We need people on this call and people in the community. We really need you to rally around the efforts that are going to be needed in for example, the uncrewed surface vehicle network, which is looking for acceptance as a decade project, within OASIS, a UN decade project. So I really hope this space has got a lot of potential for growth in many different areas with related to USVs. So I couldn't agree more.
Yeah.
And if anyone is out there that doesn't yet understand that there are these community efforts building within, for example, within OASIS, then please point them towards OASIS and the website to get involved, going forward beyond this meeting.
Yeah, I'm agree with both of you, as we've got lots of data from the Baltic Sea, from the North Atlantic, and also a lot of problems to processing them. So I hope that this community can help me to talk with each other to change our problems, our data, like we can put everything in one place, because right now there's a lot of places, in my opinion, and I just came through the internet and okay, there's some data, there are some data, the quality from this side and this side, it's similar, but not so similar. So to have something like this community, for me, it's great. Thank you for that.
Okay, thanks. Any others? So time is almost running. So let's wrap up the session. Jan, do you have final comment for both of us?
Yes, go ahead.
Okay. So thanks for coming this session. So this is the first session for OASIS best practice from the 16 UTC. The other session will start. Maybe Emmanuel give us the presentation for ocean coral, right?
Yes.
So okay, so let's close the session. Thanks for coming. Bye.
Bye.
Bye.